Welcome back, everyone. I hope everybody got a chance to have donuts on a stick. That was exciting. It's my pleasure to introduce our second invited speaker for this session. Dr. Wang is professor and chair of the Department of Chemical and Biochemical Engineering at the University of Iowa. He is well known for clever development and use of aerosol remote sensing observations for understanding aerosols, weather, and climate. He has been an active member of numerous NASA science teams, including Glory, which ended up in the ocean. That was a fun team. SUMI MPP, Tempo, Aura Aqua, and upcoming missions such as Maya. Today, he's going to tell us a story about novel methods for determining aerosol layer height and nighttime aerosol optical depth from space.
Well, thanks a lot for the opportunity to allow me to come here to share some of the work with you. This is a community that I, like to involve more. And so today I will be talking about the aerosol layer height and also the nighttime characterization of fires and aerosols. And I probably will add a bit more of to start with the fire logistics, because that's linked to the emissions and to the aerosol optical depths. So there are three elements of the fires: the heat, the oxygen, and the fuel. So far from space, in the last probably 20 or 30 years, we're able to characterize the fire-related power, time, and the location of the fire. That is actually only describing how the heat and the fuel are interacting, and you can get information for those two parameters. But the role of oxygen is extremely important in the combustion process. So we will try to first introduce you a new solar product that allows to provide some information about how the oxygen plays a role in the combustion process. So I will go back to the a little bit earlier days that we know Professor Paul Kristen passed away during the pandemic time period, and he's well known for his, for his ozone work, for winning the Nobel Prize in 1995. But he's also a pioneer that to point out the importance of the fire emissions in the tropospheric chemistry. So one of the early work is in 1979, and later had a work in 1990. So what I'm showing here, you can see on the right-hand side, it shows the time from the fire starting point to the end of the fire in terms of emissions of different species. And he drew a very kind of a little red line here to the, let's see here, is this, anyway, you can see the red line over there. It says that on the left-hand side is the flaming, on the right-hand side is the smoldering. And you can clearly see that the emissions have a distinct cycle of the lifetime of the fire. And when you have flaming, you have more complete combustion, you have more CO2, you have more N2O. But when you get to the smoldering phase, you have more methane and the smoke particles as well. So, the way we quantify the combustion efficiency, we use something called modified combustion efficiency, which is basically CO2 divided by CO plus CO2. And that number can range from, in the real atmosphere, can range from about 0.8 to 0.96 or 0.99. Although that's a largest range possible, probably about 0.2, but that small variation has a big impact on the emission factors. You can clearly see that when MCE changes from 0.8 to 1, the emission factor for OC and the sulfate and also the elemental carbon to organic carbon ratio change a lot. Sometimes it goes by a factor of 5 to 10. And you can clearly see on the panel C here, shows that when you have more MCE, larger MCE, you get a more fraction of the soot particles, largely decrease of the single albedo. So obviously, the fire is very dynamic. At a given point, the MCE can be very different. However, when you look at all the fire emission inventories we're using today, I would say probably most of them use a constant number for the fire emissions and for only the depending on the surface type and by type normally the emission inventory divided into maybe less than 10 number of surface types, and say for this surface type, this is the emission factor we're going to use. Obviously, this is very, very crude simplification. So what we want to do is try to say, can we from space to derive the combustion efficiency for the fire at the individual pixel level? So what you see here is that if you look into a little bit of the combustion science, it will tell you that the light that in the combustion process emitted by the fire is a strong indicator and it is kind of a paradigm shift on the fire combustion phase and completeness. So I'm not going to dig into detail on that. Obviously, the flaming generally occur in the atmosphere where the oxygen is more easier to get into, where the smoldering is more closer to the surface, where the oxygen is very difficult to get into. So one of the satellites that were launched in 2011 was the SUNY AMPP satellite, which has carries a day and night band that can see the lights both in day and night. And I was lucky to pass it one of those launches on the right-hand side over there. And so I was intrigued by that. And we were able to, several years able to develop a concept called the visible energy fraction, which is basically the visible light that emitted by the fire, that power in that visible spectrum divided by the total level of power. And that's become an intensive property that we hope can be able to link to the modified combustion efficiency, which is which I'm going to shoot later. So the key concept here on the right-hand side to show the key concept why the FRP does not give us the combustion efficiency is because in a given fire pixel, if you have a fire that is very hot with smaller area, or the fire is smoldering but with a larger area, they will give you some amount of FRP, but they are not going to, in terms of fire dynamics and the combustion efficiency, they will be very different. So here is the first picture that shows you the global the visible energy fraction we get from the space at nighttime. And when I saw this image, you can clearly see there are flames in the Middle East because of the gas flares. But then we also see a lot of variations of VEF by canopy type. The question is that are those correct? Are those making sense or not? So you look at more this land surface type. These are from daytime only. The one that I showed is from nighttime. You can clearly see that the variation of the MCE is actually the VEF resonates the change of the land surface type. So give you a better picture here. So on the left, you can see the VEF difference between the Northern California fires, versus the Australia fires. The VEF is very low in California fires or Northwestern fires. When you look at FRP, they look very similar between those two regions. And the reason, just as I explained, so if you look at the land surface type, you will find in the Western U.S. is because of the forests, and we know that the combustion efficiency is relatively lower compared to the shrubland in Australia. So you can clearly see this information at nighttime at the pixel level, at the regional level, and we're able to link that VEF to the MCE by doing the regression of what we know by land surface type. So to further this kind of product obviously is very difficult to validate because we are not going to put a truck in the fire and measure how much total amount of emissions we are getting in that pixel level. So here is one location shows there are 3 EPS sites that measure the NO2 and the CO on hourly intervals, and then there are fires occurred almost for 10 days. You can clearly see that the increment of the ratio between the NO2 and the CO is actually linked with the MCE very well. There are good correlations there. That's indicated that this type of information can help you to better analyze the fire emissions and hope to better simulate the black carbon or smoke particles or trace gases. So that's one of the things that we can do here. So if you look at this product, it also can tell you something about the fire lines, because all of the fire lines have to be the flaming lines. So you can clearly see on the top right that at the edge, we can clearly see where the fire lines is. When you look at FRP, large FRP values is within the parameter of the fire. This is because when the fire are propagating, what are left over is a smoldering phase. So the area is very big. Fire area part is very large, but those are the things that generate large amount of the widened smoke particles because they're in the smoldering phase. So anyway, I'm not going to, so you can give you some ideas on this one. So I'm going to skip this a little bit here. We also show that the combustion efficiency you can clearly see how the weather affects the combustion efficiency, and we can clearly see that very well and we have done analysis on that one. So anyway, this product called the Fire MCE is now in production, by NASA, and I think probably will be available soon in January to February. And I put the link over there, and we also provide a user guide, and you are welcome to use this product. And we're also now using that data build upon that algorithm for night, and then using machine learning to derive the MCE for the daytime as well. So why I'm interested in the nighttime fires, because there are multiple papers to show that the nighttime fire has increased by 30% in the past 2 decades. A couple of people already show that. So with global warming, there are lots of things that are happening at nighttime, and the fire is getting definitely more frequent and more intensive at nighttime. So because of the importance of that, we do want to look at the how the smoke are transported at night, because the fire and the atmosphere are not static at nighttime. So one of the things I try to show is that we're able to using again the light reflect the moonlight by the smoke layer to derive the aerosol optical depths at nighttime. So I'm showing here four images, and you can see 2-color image in the daytime, and then one monochrome image at nighttime, and then 2-color image and then nighttime images. What you see here is that certainly the panel E and the G give you the LED from the daytime VS product, and then F and H is from our retrievals. What you see here in Colorado on the panel G, there are a lot of the smoke in Denver. But if I'm taking away these 2 night images, and you tell me from the A to C where the smoke all of a sudden coming into the southeast part of the Denver, Colorado, it's very hard to tell. But if you add my nighttime images, where I can tell you that this smoke actually transported from the Colorado Valley to the south directly, and then geared toward the east on the second day. So the point is that in order to improve the predictions, you do need to have nighttime LED, and we do able to get some information from that by using reflected moonlight. And so that product is still in research mode. If you're interested, we can look at some cases. And then I'm going to talk from this one. Then I'm going to talk about the aerosol layer height. Thanks for Jeff Pierce for setting the stage for this. So I hope we know that aerosol layer height are very important. So we're retrieving a parameter called aerosol optical sentinel layer height. The definition is basically the altitude at which you have the largest extinction. And this product is actually online by in NASA website, and I put the link over there. So a little bit of physics here is that some of the oxygen actually absorbs the solar radiation. Some of the at certain band is actually very intense, absorption is very high. So you can see if you have 2 measurements in different channels, one is in the oxygen absorption band, another reason one is not. So you can clearly see that if in the absorption band, which I'm showing, in both cases, those are in the absorption band. So if the aerosol plume is very high, then you will reflect the photons before that photon get absorbed by the oxygen near the surface. So the higher the aerosol layer is, the less chance that the solar radiation will be absorbed by the oxygen down below. So that gives us information that if you compare with a non-oxygen absorption band, you can find the ratio. The ratio is lower, means that you have more lower aerosol layer height compared to the aerosol. If it's larger, aerosol layer height will be higher. So that's kind of physics there. So we are able to use that to retrieve the aerosol layer height for absorbing aerosols over the globe using CHOP-OMI data. So I'm showing here in the second panel from the left is our retrieval, and then on the third panel, third column there is the European standard operation product. The difference is that we're also using the oxygen B band, and we also assume the aerosol profile is continuous distribution, the extinction has a continuous distribution in the retrieval. And you can clearly see that make a difference in terms of our retrieval versus theirs. On the right most column showing the aerosol layer height from the Calypso, and those green colors are our retrievals, whereas the pink colors are from the airport. We can see that our product retrieval matches up pretty well. So why this is important? It turns out that there are there is that you see that the aerosol depth is very high. I'm showing in the bottom column row here, but the PM25 is not very high. The reason is because from our retrieve, you can tell the aerosol layer, LCH can go up to 4 to 6 kilometers, even above. And that explains why the surface PM25 is low and such. So this actually is very useful because if you look at MERA 2, which is probably the best data we have in aerosol with analysis data, you can clearly see that in those cases, they have a huge amount of the surface PM to the surface due to the false alarm because the aerosol layer height, injection height put in the model is too low, which also resonated with what Jeff was talking about this morning. And you can clearly see that by doing some corrections, you can apply LCH correction, you can correct that false alarm in the model. So in 2023, we see these cases also a lot. So we are actually looking day to day in terms of the weather forecast models on the surface air quality and how does that compare with the observations. And you can see on this particular August 16th, 2023, there are lots of models saying there are a lot of smoke over the central Canada. But you look at the air now, there are not much. The one part is because of their precipitation. That model is not doing well in simulating that. But when you look to the northwestern part of the US, again, you can see very thick smoke plumes in Montana area. But if you look at the EPS observations, there at the most is moderate, but most times they actually is in green color, means that the LOD surface PM is actually pretty good there. So why is that? Well, look at our product altogether. You can look at our MCE product that gives you that a lot of smothering, right? Because the MCE there is like 0.8, very low. You see that white smoke right there on top left circle over there. But when you look at our LED there, we achieve very high, 3 or 4. However, when you look at the LCH retrievals, you can see that in Oregon and Montana area, the LCH actually is very high, 5 to 7 kilometers. And that's why I explained to you why the surface PM there is actually pretty good. When the Oregon case, on the other hand, we choose the LCH much lower, 3 kilometers, below 3 kilometers, so PM is very high over there. So this information we hope can be useful for models. So going beyond, the Tempo was launched in the April of the 2023 by SpaceX. I was fortunate to be able to watch that launch. This one is actually far away because it's a geosynchronous satellite. So you can see there. And then after Tempo, NOAA is also planning GeoXO that will have similar capabilities carry the oxygen B or oxygen avian. So that will give us aerosol layer height information. So I think it's really a time for us to think together and work together to think about how we can use this new product for the fire emission inventories, for the evaluation of the model in terms of aerosol optical depths, as well as in terms of thinking about the aerosol transport in terms of how do we model the smoke injection height. So I list some of the data product here. The top 2 will be actually LCH product from EPIC is already operational, and the FRP product will be available in spring. And we also have research product from a Chopolumi that link over there. So with that, I'd like to thank you for your time.
Thank you very much for Professor Wang for this very interesting talk. So I have a question about the aerosol plume height you mentioned. So because this is based on the satellite observation and using some retrievals, so I'm wondering if it can also help to estimate the fire injection height of this product.
Yeah, what the injection height?
Fire, the injection height, or so, somehow like the volcanic volcanic eruption or something like that. Is it can be helped to do some of those estimates?
You can see, for example, this example here on the top left, those are MCE. The dots there are MCE, basically active fires in terms of their combustion efficiency. And you just look at the other one there, you can see there are a lot of the inhomogeneity in that smoke plume. And when you look at our retrievals down below in the top in the bottom left, we do able to capture that inhomogeneity. You can clearly see some of them are only get to 2 kilometers, but some of them also get to the 4 or 5 kilometers. So I think this information can be useful to specify injection height. It's really dependent on how we specify injection height, because what solid in this case retrieved is really a ending results of the process. So I would think that this can be very useful for you to specify parameters or even directly use them in the fire source region, in the fire region, the specify injection height. So we have not looked into that yet. So but this product is now available for the last 3 years in North America.
Jun, I have a question about the first part. You're showing that MC correlates very well with vegetation type. And in our typical biomass burning inventories, we have emissions factors that also vary by vegetation type.
Yeah.
So how much more variability are we getting in emissions factors with the addition of MCE beyond what we would already sort of be estimating just based on changes in vegetation alone?
Yeah, so that's a good question. That's the 2 slides I kind of skipped. So if you look at this campfire, it will tell you the FRP, the most likely FRP, look at this case here, is actually occurred in the November 9th. But if you look at our VEF, is actually occurred most intensively on the November 11th. So obviously, there are a lot of changes in the VEF, which based upon VEF, we can derive, there are a lot of changes in MCE. So the fire is very dynamic, and you can clearly see that the reason is because on the November 11th, the humidity of the wind speed go as low as 25%, and the humidity, and the wind speed goes as high as 5 meters per second. 5 meters per second. You can clearly see there is a panel shift in terms of how the wind is coming to fuel those fires. You get a much drier and stronger wind speed. So our side is actually the retriever is telling you that there is more combustion, more combustion. So, but if you look at inventories here, the fire emission inventory here, I would say we are just using 1 parameter for the emission factor because they're same surface type. So this one gives you a dynamic. This one gives you an opportunity to calculate that emission factors as a function of their lifetime of the fire, as well as the pixel level. And let's get back to the Paul Froden's slides way early. Shows that the emissions changed a lot as a function of the lifetime of the fire. So I think this will give you, description of the emission factor changes by the weather systems and throughout their lifetime.
Thank you. Let's thank our speaker again. Our next speaker was Dr. Zhang, research scientist at CIRES, and she is going to tell us about the NOAA's UFS model.
Good morning, everyone. Thank you for attending my talk. Today, I would like to talk about the development and application of NOAA's global aerosol forecast system. First of all, I would like to acknowledge all the co-authors and collaborators from NOAA, GSL, CU Boulder, and NOAA ARL, CSL, GSL, and NOAA EMC. We know that the aerosol either coming from the anthropogenic activity or coming from the nature sources. They both play important role on impacting on the human beings and raise the concerns about impact of aerosols and more complex chemistry on weather forecast, subseasonal to seasonal prediction, and climate change. And the role of the aerosol in the aerosol radiation balance has been investigated since the early 1990s by using the KITE model. However, most of the numerical weather prediction system, especially the operational model, are still using the average effect. For instance, the climatological of like MERA2 aerosol data to quantify the aerosols on the radiative balances, which has not involved the importance of the aerosol on the weather and S2S scale. We know that NOAA's operational air quality prediction in National Weather Service contribute to protect lives at the United States, and which requires sustainable development and improvement of the global aerosol forecast system for air quality predictions. Now let's review the development of the global aerosol forecast system at NOAA in the last several years. before 2020 September, what we have is the UNGAC system, which is based on the previous global forecast system at UNSIP. And since 2020 September, that we launched a new global forecast system, which is named the UFS-Aerosols, which has been implemented in the UNSIP's UFS version 12. And this new system is based on the new weather model by using the finite volume dynamic code FE3 developed by GFDL with an updated physics scheme of version 15. And the horizontal resolution has been increased from 100 kilometer to 25 kilometer globally. And this model for the aerosol component is based on the go-car in Wolfgang, however, with some updates by the NOAA OAR labs. It's not, which including the updates in the Fonseca scheme, and also some of the anthropogenic and fire emissions and the wet scan engines. Here is the performance comparison of this gas aerosol compared to the ONGAC model. And it's the daily AOD that's validated by the Aeronet site for 4 months in 2019. We can see the correlation coefficient of gas aerosol has been significantly. Most of the sites are larger than 0.6 compared to the previous one. Most of them are below that. And early this year, we launched another updated version at UNSIP for this 12.3. Okay. Yeah, it will be better. Oh, thank you. Yeah, we launched a new version of 12.3 in at UNSIP, which with some improvements in the AOD calculation and fix some bugs. We can see with this a dash blue line of this new version, the overestimate of this fire OCAOD has been significantly improved over fire regions, especially like California and some of the North American areas. Here are some of the other applications of this gas aerosol in UNSIP operation. And this is the Canadian fires that we know this summer, which has significant impact on surrounding areas. The gas aerosol model is able to predict this fire impact for the within 1 week when we can see this impact over surrounding areas. And the other application is that we can see here is the Sahara dust plume. I don't know why it did not work. Sorry. That you can see that's the Sahara plume from African with the long range transporter to impact on the United States has also been captured by this gas aerosol prediction. And the other experiment that we have is the Tango volcano eruption. Yeah, so we add estimate of SO2 and volcanic ash into the Tango volcano, and then we can estimate the global impact of this volcano ash. And the other application is the boundary condition for the UNSIP CMAC operational model. Yeah, since 2021, that we have a new project and launch a newer development for the UFS model system, which is the GAPS version 13. And it is newer model. The major update is the vertical resolution has been increased from 35 layers to 127 layers. And meanwhile, the aerosol components has been used the NASA second generation go-car. And the other important thing is that this model is fully coupled with ocean sea ice and other components, and it's a two-way coupling which can improve, which can include the aerosol feedback on the meteorological field. And for this, gas aerosol is only one-way coupling, and the aerosol feedback is still based on the meteorological of MERA2. And with this update, now we can perform, we can apply this to the subseasonal to seasonal prediction. And here is an experiment of the UFS prototype A that we run 7 years, twice per month for 35 days as to as forecast. With this UFS model, here's some preliminary result that you can see. The results are very encouraging, even though that there are still some positive bias over North America, which is due to dust in the 3rd and 4th week.
And recently, we launched a new experiment to try to include more ensemble members into this UFS aerosol for the ensemble prototype 4 experiment. And in this experiment, we performed 2 different experiments. One is EPA, which is using the same configuration as the previous PA, and the other is the EP4B. That's we using an updated FONSADA scheme developed recently by Fixum Bark related to the soil moisture. And we also using a scaled Q-fed fire emissions. And we know that because the 10 ensemble members, we only has the perturbation in the meteorological field, which means it would only impact on the dust and sea salt emission because they are highly depending on the meteorological field. Now from here, we can see that with this updated dust scheme, it significantly reduced the MSE of the dust ALD and total ALD. Meanwhile, the ensemble mean, the dashed line is much better for dust and sea salt compared to the control member, the solid line. So it also suggests that in the ensemble rounds, by adding the perturbations in the emissions of the species may help to get much better predictions from these ensemble mean members. And this year we have a collaboration for several OER labs like AIL, GSL, and GFDL, GML, since we are trying to, other than this operational global aerosol forecast, we are trying to develop a research version of chemical model that's coupled with this weather model. And then so we based on the gas aerosol. However, we changed the infrastructure from NOAA by using the CCPP, the common community physics package as the infrastructure, since this can help to break out the aerosol modules and insert them in the physics suite, which would be better to get interaction between the chemistry and the physics, especially in the future when we are going to including the aerosol indirect feedback. And at the same time, other than the aerosol component, which is coming from the gas aerosol, we are going to add other complex aerosol scheme and the AM4 and some of the other gas-phase chemistry like AM4 and some of and others. And meanwhile, the global aerosol system will also be implemented. Here is the framework about this UFS-Chem framework. For the chemical part, we name it as the CAPChem, the configurable atmospheric chemistry. So other than the aerosol component I mentioned from aerosol, from gas aerosol, we will also have the gas, we also have the smoke dust and the kraken from EPA, CMAC that we plan to collaborate with Havana. And for the gas phase mechanism, other than the greenhouse gases, we will add in the chemistry from RACAN and the AM4 from GFDL. And we also collaborate with Mary and Carl to add in the Mechan system into this model. So other than that, the AIL is leading the development about a tool named like Nexus to pre-process all kinds of emissions as the input. And we will also use some utility to set up the post-validation. Here's some preliminary results of the UFS-Chem, which is based on the gas aerosol component. Now we can see compared to the UFS aerosol model, that the gas aerosol has better performance in this S2S fire OCALD prediction. So one the reason may be that's in the UFS-Chem, we have the prime price module there. However, in the UFS aerosol, which is based on the NASA second generation Go Card, they don't have this prime price module, and which may help to improve this OCALD prediction. And the other reason that we dig into and then we find both of these two models are using the GBB-PX fire emission from NOAA operational, which has been developed by NOAA Nestis. However, they provide two different products to us as the input, since the NASA Go Card need to use the 0.1 by 0.1 degree products as the input, and they use an internal like maple system for the horizontal interpolation. For gas aerosol, they provide us the product is based on the model native graded. And we can see they have like some big difference over these African areas. That is looks like this 0.1 by 0.1 degree product is much higher. then this model native graded resolution. So considering the resolution and uncertainty when agree from these different kinds of the fire products or satellite observation, and also considering the diversities in different fire emission products, for instance, GBB, PX, QFAT, and GFAS, and somehow their fire emission may have large difference and even a factor like more than 4. So here we funded by a WPO project, and we are trying to improve the sub-seasonal to seasonal fire emission and weather forecast. And the challenge is how to get a better estimate about the fire emission in the next 35 days in the real-time or operational forecast. So before doing that, the first step, we are trying to generate an ensemble fire emission that's based on like 7 different fire products. And from the preliminary testing, we can see that this ensemble fire emission, it's very good compared to the current operational GB version 3 and 4 in predicting the fire OCLD. So I will stop here for some questions and not go through the summary details. Thank you very much.
I will look at how your model is simulating the vertical profile of aerosols. Have you looked at it at all?
The vertical profile?
Yeah.
Yeah, I think this is a really good question. And currently, we for depth aerosol, we have compared with the ATOM, the aircraft's campaign, which shows the vertical profile compared to the ATOM. We still have some missing in the aerosol plumes. That's why you mentioned like the aerosol plume height. Yeah. I think this may be related to the injection height simulation because we are using a 1D plume price module. So it's not based on any, satellite data or something. Mm-hmm.
Thank you for a great talk. This is very, very impressive. I was surprised by the very super high resolution, like 0.0 and 0.1 degree and like more than 100 vertical level, something like that. But how it does take long to run your simulation? Can I get any sense of computational cost aspect?
Yeah, sure. Now, currently for 384 resolution, which is like 25 kilometer globally, if we go to like a 25, we go to 65 layers for 24 hours integration, it may take less than half hour, sometimes like 20 minutes with more than 500 processors. So it means that's the computation cost is highly depending how many like tasks you are going to use.
Yeah.
I have a question about sort of the long-term plan and timeline with UFS-Chem. For example, if I have a new PhD student starting, I would have maybe had them modeling with WRF-Chem, but now the sort of development of that at NOAA is no longer being continued. At what point in the future do we have that kind of user meeting, user support, community portability of the code for UFS-Chem sort of on the horizon? Is that a year or 5 years, or where do you sort of see that?
I think that's a very good question because for this UFS community, what I show here is the global results. We also have the regional part, for instance, the RFS, which is based on the same of this UFS framework. However, they are using like different physics package. It's like the physics scheme is different because here we are using GFS 17, and for this region model, they are using like the physics from Hurricane. So I think now we have a new organization and like EPIC. They are in charging of this training of all this model and the tutorial and the document. And some of that, I think if your students are interested in that, because they are all open source model, so you maybe pay attention to the EPIC, they will have like more of those things. All right, thank you.
Our next speaker is Duncan Watson-Parris, assistant professor at UCSD. He's going to be telling us about AirChemMIP2 and deciphering the roles of aerosols and chemically reactive gases in climate. And
got it. Perfect. Thank you very much. Nice to be here. So I want to talk about, it's kind of a, less of a science talk, more of a advertisement, I guess, and a call for input from the community. So I want to introduce AirChem MIP2, and to do that, I'll kind of give a brief retrospective on the goals and achievements of AirChem, the original AirChem MIP and CMIP6. I'll give you an overview of the current status of AirChem MIP2 and then discuss the future plans and the timelines for AirChem MIP2 and CMIP7, and hopefully leave plenty of time for discussions. So AirChem MIP originally, so there's this nice overview paper and protocol definition paper from Bill Collins and GMD back in 2017, laid out 4 high-level scientific questions that they were looking to address. How have anthropogenic emissions contributed to global radiative forcing and affected regional climate over the historical period? So there's kind of a radiative forcing element. How might future policies on climate, air quality, and land use affect the abundance of NTCF? So this is CMIP jargon, near-term climate forces, including aerosols and chemical species, and their climate impacts. How do uncertainties in historical NTCF emissions affect radiative forcing estimates? And how important are climate feedbacks to natural NTCF emissions? So those are kind of questions that you can get at in these fully coupled models. As part of kind of reflecting on the achievements of that and looking to develop AirChem MIP2, I wanted to highlight that, you know, I think they did a great job, and the results that got turned around pretty quickly. There was, I don't know if any of you were involved in AR6, but the gap between these simulations coming out from CMIP6 and actually having to be published and then cited for AR6 was pretty tight. But these papers from Jill Thornton and Chris Smith quantified, using these AirChem MIP simulations, quantified the contributions of component emissions to present day radiative forcing and historical, so radiative forcing on the left and historical temperature change there on the right. And so all of the plots that you see of this kind, in particular from chapter 6 of the AR6, sixth assessment report from the IPCC, are building on these AirChem MIP simulations. There's a paper from Griffiths, Murray et al. In ACP looking at the time evolution of, for example, the mean tropospheric ozone burden, both over the historical and into the future, and what the implications of that are then for aerosol lifetime and other air quality measures. And there's this nice paper from Jill Turnock et al. On Earth's Future looking at quantifying the trade-offs and co-benefits of climate and air quality changes from different future pathways parallel to SSP 3.7. So there's this future pathway under which aerosol emissions are actually pretty high. And we had a complementary pathway with low aerosol emissions and low NTCFs in AirChem MIP that enabled us to then look at the trade-off between radiative forcing on the y-axis and change in various air quality measures on the x-axis, so either PM2.5 or exceedance of ozone levels, and really kind of dig into these very relevant policy questions. And then finally, there's another paper here in ACP looking at the quantifications of different non-CO2 biogeochemical feedbacks. So these feedbacks are potentially important, but they're very poorly understood and constrained, partly the difficulty of running these chemical models in a fully coupled setting, but enable us to estimate the effect of, for example, lightning, NOx, wetland, methane, etc., on forcing from a change in temperature through, for example, greenhouse gas warming. Another way of kind of reflecting on this is, you know, these are obvious successes and these papers are well cited and will be important into the future. There are a lot of simulations as part of AirChem MIP. I don't expect you to read all of these, but these are all the simulations that were requested as part of the protocol that Bill laid out. And I went through actually and just counted all the papers that cite this paper and which experiments they used, and then conversely looked at which models ran which simulations. And so you can see some interesting things that, you know, the PI CLIM control is the baseline one that most models ran that. Very few models ran the NOx experiment or the NH3 experiments. And actually, they're broadly correlated, which is kind of interesting. So I think there's a kind of reflection of interest from the modeling community versus interest in the people who use those models to write papers. But this is kind of at the forefront of our mind. There's a lot of modeling effort goes into here, and so this is kind of at the forefront of our mind as when we're developing Air-Chem MIP2. So this has been registered as a new project for CMIP7. Stephanie, Fiona, and myself are co-chairing that. Stephanie's in GMR and Fiona at the Met Office and Exeter in the UK. And we're currently in the process of scoping out the scientific goals. So we're coming to these meetings, going to AGU and CCMI and other places to get community feedback and inform that experimental protocol for the next round of experiments. And we're also liaising with other MIPs. So there's overlaps with RF MIP, who do a lot of forcing experiments. There's overlaps with DA MIP and so on. The broad goals are similar to the original. I don't think we've solved any of the original ones, but we've made progress. And so, we're broadly looking at what future climate penalties are expected from, actually, I'll start from the bottom. I'll start from emissions. So I think, if we think about how emissions, how our process understanding has advanced on anthropogenic emissions, contributing to global and regional atmospheric composition changes, reactive forcing, and climate responses. This is very much kind of the focus of this work and process modelers in the community, I think. And then we think about how those compositions, what's the relative importance of climate changes and emissions for atmospheric composition and air quality, responses and feedback. So how important are climate feedbacks to natural emissions composition? And then linking out to kind of thinking about the links to AR7, what future climate penalties are expected from improving air quality, what are the trade-offs for climate benefits arising from policies for improved sustainability. And so those are very pertinent questions, right? I don't know if any of you have been involved with any of the shipping emission stuff that's been happening, and people have been discussing the various trade-offs and what the implications of that might have been. So they're the guiding kind of questions. The framework we're building around is very familiar to many of you, I'm sure, looking to understand these various pathways. But broadly, the goals are to understand the role of historical emissions in composition changes, future changes in atmospheric composition, air quality, and climate from different future pathways. Process understanding, and this is where IAMA and other process modeling groups come in. How we updates in our understanding of composition and forcing, and then improved understanding on these biogeochemical feedbacks. So when you get a climate response, what does that mean for natural emissions of dust and sea salt and so on? The CMIP system, so this is a slightly it's an interesting organization. It's still kind of feeling it's coming into a new phase now, and it's interesting being on the inside of it for the first time. But they've decided that there will be a set of fast track simulations that they will focus on first, that are intended to inform AR7, so the next IPCC report, to prevent the previous problem of having all the data coming at the same time and trying to get papers out so that they can be ready for the assessment report. So we've proposed a number of fast track simulations which we feel are most useful in that regard. So the fully coupled historical simulations, so HIST-PI aerosol and HIST-PI SLCF. So these are fully coupled pre-industrial aerosol. So you run the full historical simulation, except you just have PI aerosol. And so this is a kind of all except one simulation. It mirrors the DA-MIP HIST AER simulations, which only have historical aerosol, and enables us to look at nonlinearities in the aerosol response through the historical period. We will have some sort of future projection with a reduced short-lived climate forcer element. So we'll have some future projections with changed aerosols to explore those air quality trade-offs. Number of fixed SST experiments to quantify forcing. So we'll have forcing simulations for SO2, BC, NOx, methane, etc. And then a few, probably 6 or so fixed SST experiments to quantify those biogeochemical feedbacks. So looking at PI chem, 2 times dust, 2 times sea salt. We are actively seeking feedback from the community on those goals, on those questions, on those simulations. Questionnaires here. I'll leave the QR code up afterwards if you're keen to engage, if you're a modeler, or if and you're thinking about running some of these simulations, or if you're, interested in using some of these simulations to answer some of the questions in your research. We very much welcome your input, either backwards thinking about the previous experiments or looking forward to MIP 2. If we can have that feedback by the middle of January, that would be fantastic. I think, yeah, so that's what I wanted to say about that. But I wanted to use this opportunity really. So rather than asking me questions, I want to ask you questions if I can, and maybe start a little bit of discussion around, are these the most pressing questions that the aerosol community want answered by these, pretty expensive sets of fully coupled simulations? It's not very often you get to run these big class of models for this long. Are these the questions that you want answering? Is there something missing? Is there a burning question? Is there a relevant topic that you feel has not been addressed here? What are the key diagnostics? I was in the modeling session yesterday lunchtime. What are the key metrics that we want to be able to compare these models with and against real observations potentially? AOD would be nice, daily AOD for most of the models, but is there anything else? How can we harness and link to the more detailed process-based models that most of you guys are working on? Are there opportunities to have reduced complexity or maybe smaller set of increased complexity simulations? What should be the barrier to entry? What should be like the minimum requirements for a model to run in terms of chemistry and aerosol representation to run these simulations? Yeah, and so I'll put that to you, and hopefully you can give me any feedback. If you have any clarifications, of course, I'll be happy to answer those as well. Thank you.
Yeah, thanks for leading this effort. So I don't know really well about climate models, but the Aerocom community has been doing the model comparison for on a reanalysis mode for a while. And I think what they are leading up to is really want to look at I think there are papers to show that AOD's agreement is getting better, but the aerosol vertical profile, what they call anyway, they come with some metrics there is maybe mass weighted, the aerosol air height, instead of looked at the profile a lot, just look annually or zonally averaged mass weighted aerosol vertical profile. Even that, they find the biggest difference there. So I would think that the vertical distribution somewhere over there could be very interesting to compare among different models.
Yeah, that's a really interesting point. One of my first papers in this was looking at vertical distribution of aerosol. It would be nice to be able to pull some of that out. 3D fields tend to be a big ask because they take up a lot of space. But it might be possible if we can think of a simple 2D diagnostic that we can ask, then that would be ideal. But maybe, yeah, I'll make a note. Thank you. That's a good point.
Okay, yeah, so one challenge always for global modeling is the emissions of aerosols. And we have seen that with fires, the inconsistency in the historical, then again in the future. I mean, this is not for you to decide on it here, but maybe there's something you can say about that. We really need to improve that part to have some good estimations. Do you have any insights on that?
There is an emissions MIP that I'm aware of that looks to run at least a historical simulation under different aerosol emissions, exploring some of that uncertainty. It would be good to make sure that they actually are also, I guess that they have diagnostics to diagnose the forcing, but it would be good to make sure that we're linked up with them to make sure that we can get the information we need from that.
Yeah, you could, for example, have a experiment that uses different aerosol emissions that is like maybe climatological or, somewhat from a different source. It could help with that uncertainty.
Right. So that if it's not an idealized simulation, then it comes under the remit of the scenario emit people. So they come up with these various kind of scenarios of different emissions. And I think so 370 as opposed to 585 was really trying to explore the differences in regional emissions patterns, particularly in East and South Asia. But that's a good, yeah, that's another good point. Thank you.
One thing I would point out is amongst all of the MIPS from last time, it wasn't actually possible to separate out aerosol-driven changes in clouds from temperature-driven changes in clouds, forcing in feedback. So that's something we should give consideration to. We had a paper on that where we tried to look at the long-term trend in the North Atlantic, and there weren't all the experiments we needed to be able to do that cleanly. We had to back it out indirectly. Too much to go into here. It's quite complicated how we had to do it, but it'd be worth just checking whether we have amongst all of the MIPS a way to do that separation, because a lot of the trends in clouds now are driven by feedback, not aerosol, but they could be wrongly attributed to aerosol. So I think that's something we should discuss.
I know Chris Smith has been working on this PRP or partial radiative perturbations, radiative kernels, things like that to try and get around this, but it'd be good to know what was missing and what we need to make sure we include.
Closing us out here, our final speaker of this session and of the meeting, Pietro Vannucci. He's a PhD candidate at UC Berkeley, as well as an ORISE fellow at the EPA. And he's going to tell us about temperature-dependent composition of summertime PM 2.5.
The laser, it's the red button. Yes, great to be here to be closing out this conference. I'll dive in by acknowledging my co-authors, both at the EPA as well as UC Berkeley. Received a lot of help with this, some of us in the room today. And I received a lot of conceptual and computational help to accomplish this project. So I'll be talking a little bit about how we've been using atmospheric models to help us understand the temperature dependence of PM 2.5, but also how looking at this temperature dependence and viewing this relationship can actually help us refine our model design strategies. I'll be using outputs from CMAC version 5.4, running with the newly developed CRACM chemical mechanism. And I'd be happy to chat more about the model setup after, but I don't want to dwell too long on the specifics because I hope to present here a kind of case study that is more generalizable than that. So we'll be comparing these outputs to observations from the EPA air quality system. And we'll be looking at the domain of CONUS or the United States for the summertime, June to August of 2019. And I can start by saying from the observational side of things, we obviously care about understanding the drivers of summertime PM 2.5, specifically what is associated with high concentration events, what components, which processes form them, and then to what extent we can hope to control them now and going forward. And so why study this at all? Because I think that there's really interesting things happening here. We can begin with the observation here. This is looking at PM 2.5 versus temperature. We're looking at specifically Washington, DC, but this is a common story in this part of the world, not specific to Washington, DC. What we're looking at is this very strong, robust correlation between PM 2.5 and temperature going back at least 20 years. This is just daily average PM 2.5 binned by temperature deciles. And we can see that actually not only is there this relationship that's been strong, it's actually been weakening. Back in the day on the coldest summertime days, we would see 10 microns per cubic meter, and at the hottest, something like 30, a huge increase. And it's weaker now, but in relative terms, it's still quite significant. In the most recent 5-year sub-period here, the purple line on the bottom, we see that we're still going from something on the order of 5 to something on the order of 10 microns per cubic meter from the coldest to the hottest days. So having observed this, we thought it would be an interesting investigation to pursue to see why this was happening. And in answering this, we found that ammonium sulfate aerosols could be to blame. So what I'm showing here now is this plot analogous to the one you just saw, but now instead of total PM 2.5, we're looking specifically at ammonium sulfate. And we can see that these reductions that we've seen in temperature dependence are actually linked specifically to ammonium sulfate more so than other components of PM 2.5. Now, there are some chemical reasons for why we might expect an enhancement of SO2 oxidation at higher temperatures, but the most compelling reason we found for why there was this drastic change was actually in SO2 emissions themselves. So in the Eastern U.S., we have a lot of coal-fired power plants. They used to have even more. And on hot days, what would happen is air conditioning demand would go up with that electricity generation to match, and the combustion of coal would then generate SO2, increasingly so at higher temperatures. Then, as we have been shutting down coal-fired power plants through the years, we found that these SO2 emissions have dropped in absolute terms very significantly, but their dependence on temperature has remained. So the left panel here explains the right panel, and the right panel explains what we've noticed in total PM 2.5, this dramatic change. So this is interesting, and however, ammonium sulfate aerosols are not the only temperature-dependent component of PM 2.5. Here we go. So obviously there are other components. Much of those are organic aerosols that are generated from temperature-dependent biogenic VOC emissions. So we can imagine thinking about the total response of PM 2.5 temperature, and that's what I'm showing in these bar graphs here on the left in red, in micrograms per cubic meter per degree Celsius. And at the beginning of the millennium, this was something on the order of 2. And the bulk of this could be attributed to ammonium sulfate aerosols, with the remainder explained by organic aerosols, or roughly so. Obviously, there's not as much data collected as 1 in 3 as opposed to daily for speciated PM 2.5. So there's some uncertainty in here, but roughly these two components are explaining the bulk of the temperature dependence, and ammonium sulfate used to dominate. We then fast forward 15 years now, we're looking at the period 2016-2020 now. First of all, we notice that the absolute value of the PM 2.5 dependence is much lower, now closer to something like 0.6 micrograms per cubic meter per degree Celsius. And now it is ammonium sulfate that is the minor fraction, and the bulk of this temperature dependence is now dominated by the behavior of organic aerosols. And this is a success story in our reduction of SO2 emissions and coal combustion, but it also makes our job a little bit harder, because now if we're thinking about this green bar here, there are so many more precursors, so many more processes that are driving these, and it's going to be a lot harder to target this fraction. So having made this observation now, I decided to turn to atmospheric models to see how they view these relationships, and if they could help us probe the future of organic aerosols and their response to temperatures, and try to figure out what some of these drivers might be. And we can begin just now looking at the Eastern U.S. again, and every dot on this map represents an AQS site. And now we're just averaging over the entire summertime period, June to August 2019, and we're just asking, how does the model represent organic carbon PM 2.5? And what we notice right away is that there's these widespread overestimations, something on the order of 0.5 to 1 microgram per cubic meter. The model is overestimating the amount of organic carbon consistently across the Eastern U.S. And I thought this was interesting on its own, but it becomes even more compelling when we consider that if we look at the other temperature-dependent component, sulfate, we see the exact opposite trend. Now over the same domain and of roughly the same magnitude, again, something like 0.5 to 1 microgram per cubic meter, we see that the model is missing sulfate consistently in the same areas where it was overestimating organic carbon. And we can visualize it spatially like this, and we can also think about it in terms of normalized mean bias, now dividing by the average and finding that at the lowest temperatures, the model actually does quite well with both organic carbon and sulfate, PM 2.5. But as temperature grows, the biases grow divergently in a linear fashion in almost a mirrored way. At the hottest temperatures, then the hottest decile of temperatures, we find that the model is overestimating organic carbon by something like 50 to 75% and underestimating sulfur by something like 100%. So this is clearly something going on here linked to the processes, and we can look at it in this manner, analyzing the entire data set at once, but we can also think about it as the individual AQS sites themselves. And that is what I'm showing here. Every dot in the scatter plot now represents an AQS site in the Eastern U.S. And on the y-axis, we have the modeled slope of PM 2.5 versus temperature, what the model thinks it should be. And on the x-axis, the observed. Comparing thus the distribution of sites to the one-to-one line of agreement shows us that for sulfate on the left, all of our sites are lying below and to the right of the one-to-one line of agreement. Essentially, every single modeled slope is way underestimating what observations tell us the increase of sulfate with temperature should be. And it's doing so in a way that it's increasing as the observed slope increases as well. Then on the right side, we're looking at the same story for organic carbon PM 2.5, and we then see the opposite again, that most, now not all, but most of the AQS sites now have a modeled slope that's far too large compared to the observed slope. So we're really missing this almost across the board in these complementary ways. So looking at the model output like this now kind of compels us to consider what changes to the model could be made to try and address these biases and try and create better agreements so that we can return to the original question of probing the nature of organic aerosols in the summertime. And we tried a lot of things. We tried a lot of things that aren't even on this slide. But for the sake of time today, I just want to highlight two specific things that we tried that were particularly encouraging. And I'll begin on the sulfate side by saying that the current model iteration before we tried this featured gas phase and cloud phase oxidation of SO2, but did not have particle phase oxidation. So one thing we wanted to try is to see like how much could this pathway, aerosol phase uptake of SO4, could that help with generating better sulfate predictions? And you might ask, well, this sounds like an important pathway for sulfate generation, but how is this temperature dependent? And the answer is it doesn't need to be if the SO2 is temperature dependent. And all we're doing here is converting the SO2 that is already temperature dependent into sulfate at higher rates. And then another intervention that I want to talk to you guys about today on the OC side then is something we tried to do with photolytic SOA destruction. Now, instead of targeting organic carbon production, we're targeting removal systems, and we're targeting specifically photolysis because of it, again, not direct impact with temperature, but because it's a proxy for irradiance, for sunlight. So on warm, sunny days, the sun is shining brighter, the temperature is hotter, we're getting more photolysis. And that is a way that we decided we could try to target the overestimations of organic carbon with temperature. Again, among many others, which I'm happy to chat about after. So we can think about how we can assess the impact of these interventions on model design by returning to the first scatter plot I showed you. You can imagine drawing a line of best fit throughout distribution, and that is the same thing that I'm showing on the right, just rescaled. And again, we're way off from the one-to-one line of agreement. But if we imagine rerunning the model now with the particle phase sulfate uptake, and then recalculating those slopes, we now find that we can bring the model much closer in agreement with the observations, getting really close to that one-to-one line of agreement, thus showing that by introducing this intervention, we are able to have the model produce a lot more sulfate and do so in a temperature-dependent manner, which is extremely encouraging to see. However, it's not all good news if we turn to the organic carbon side. And now again, I'm showing same visualization, a line of best fit through distribution compared to the one-to-one line is sitting neatly on top of that. And the problem is that when we boost sulfate production, we also boost organic carbon production. This is because sulfate in the particle phase can increase the aerosol liquid water content. It can increase the acidity. It can promote organic carbon formation in a number of pathways. And thus we find that when we introduce this intervention to help out the sulfate, we ended up worsening our organic carbon overestimations by quite a good bit. Again, nudging the needle in the wrong direction. And this wasn't all bad news though, however, because just how one intervention made things worse, the photo destruction was actually able to help bring us back down, help lower those modeled slopes pretty much across the board, helping us approach a one-to-one line of agreement. So it's clear that these are processes that we can target and we can influence at the correct magnitudes. And what will be the next steps will be to determine essentially how we can develop synergistic interventions to ensure that we are addressing both biases at the same time, increasing pathways to produce sulfate and to do this in a temperature-dependent way, and also removing organic carbon and the extra organic carbon that is generated by that extra sulfate. So we'll be thinking about this in a synergistic way. But I believe that a combination of model interventions can address these because we have seen that we are able to move this and address both temperature-dependent biases in both components simultaneously. And it doesn't necessarily have to be these interventions. I'm proposing here a sort of framework for how to think about this, but we want to make sure that what we're implementing is atmospheric irrelevant and not just an empirical correction. So it's going to take perhaps a lot of iterations to find that right balance of which interventions are able to address these biases, but also make sense. But this is very important work, I think, because to achieve these adequate model presentations of these PM2.5 components and their response to temperature is going to help us to be able to go back to the question of what organics are controlling high summertime PM2.5 in the US, and will help us make these predictions and develop, hopefully, control strategies now and then, of course, in a warmer future.
Cool talk and really cool to dig into the chemistry and physics underneath some of these trends. So when I think of the temperature dependence of OA, the first two things I would think of would be delta HVAP, the heat of vaporization, and the temperature dependence of emissions from Megan. And I was surprised to not see those two investigated. So is there a reason why you ruled those two out?
I wouldn't say I've ruled them out. I would say this is the first steps, and this is just about establishing kind of like a procedure for how we could implement these changes and how we could then assess their efficacy. And I think that, looking more into the physical side of things, it's not where I have background, but it's where I definitely think I want to explore this from a number of different directions. And so I don't want to limit, future experiments. Yeah.
So my question partially overlaps with Jeff's, but it seems to me one of the keys in being able to predict, I'm over here, sorry.
Thank you. Sorry.
It seems one of the keys to being able to predict the temperature dependence of the OC depends on the ability of the model to get the primary versus secondary fractions right, and and being able to then predict like the data with the delta HVAP, right, the semi-volatile behavior. So I'm curious if you have any sense of how well the model is getting that right. I know you don't have OC split into primary and secondary, but we still have an idea of how much sort of secondary we expect.
Yeah, so I think in general, my gut feeling here would be that the secondary matters a lot and a lot more, because one of the interventions we tried that I didn't talk about here was when we were looking around with different biogenic emission inventories, looking at comparing Megan to BICE, for example, we were noticing that just that choice alone, changed our overestimations by so much. It had a huge impact on the organic carb production. So I do think that a lot of this is linked to BVOC emissions, more so than anything. And I think that, continue to explore this in a variety of domains, maybe with the different vegetation, with different biogenic profiles would help us arrive at that question about primary, secondary. That's not something we've specifically looked at yet, though. Yeah.
Thank you. We're going to have to wrap up the Q&A here because we need to wrap up the conference because some people have their bags ready and are inching towards the door to get to their planes. And Faye is already on her feet, giving me the
I'll be around that
signal. But yeah, hopefully you can ask Pietro questions later. And thank you again for your presentation.
Thank you, everyone. I'm sure you can continue the discussion after the session, but I know several people have trains and planes and whatnot to catch. Thank you for the last 3 days of a very stimulating conference and discussion. I always love this meeting. It's wonderful to get into the details of aerosol mechanisms. So on behalf of the Technical Program Committee, Andy and I would like to, thank you again and safe travels and enjoy the rest of 2023.
Yeah, maybe also thanks a lot to Sandra and her team for helping organizing this conference, for the program committee to help putting together a very nice program, bringing in speakers on the whole range of topics, and the California Aerosols Board for sponsoring the conference. So have a good travel back. Thanks.